Now, if we want the expression for the angle between PQ and PR, here's PQ, here's PR. You got some angle in here. That should be very straightforward because that's simply related to the definition of the dot product, something you simply need to know. And get my camera back. No, I'm not. Okay, well, anyhow. Okay, expression for the angle between PQ and PR. Again, very straightforward application of the definition of the dot product. That's fundamental, and you've done these problems, so, you know, I question whether WebAssign is really inspiring you to learn what you're doing, okay, by doing it. And if it isn't, you need to make sure that you make sure that you do it, if WebAssign doesn't. Okay, so V dot W is magnitude of V, magnitude W cosine theta, definition of the dot product. You can easily solve that for theta, which is the angle between V and W. And you can apply that to PQ and QR, and you get the inverse cosine of the dot product divided by the product of the magnitudes. And that should be instant and straightforward, okay? Okay, so what's the projection now of QR on AC? Okay, projection, you got to understand that. You got to understand the picture of the projection, how you get this triangle here with angle theta. With this projection line, you get the scalar projection of V onto W, and then you multiply that by a unit vector in the direction of W. So anyhow, your V cosine theta, magnitude of V cosine theta, is V dot W divided by magnitude of W. That's your scalar projection. Right there it is, V dot W divided by magnitude of W. I think in terms of multiplying V by a unit vector, W over magnitude of W, unit vector in the direction of W, and that automatically gives you that side of this little triangle. And then the vector projection of V onto W, you multiply the scalar projection by the unit vector in the direction of W. Okay, that's another way to write it. Now if you substitute for this, substitute this expression, you get the expression I've written before, and you got the magnitude of W twice in the denominator. So the expression you see as a formula has a magnitude of W squared, which I think is a terrible idea. It's a way to compute without understanding. I like this, or what you get if you put this expression here in this and don't combine the magnitude of W. So you're seeing the two different ways the magnitude of W is involved in doing this vector projection. So anyhow, the vector projection of QR on AC then is very straightforward. Right there you have it. Okay, you just use the same idea. So here's the scalar projection, and here is a unit vector in the direction of AC. Okay, now we want the directional derivative in the direction of AC. We've got a problem because I can't put this up on the board. Let me see if I can compress this just a little more. I don't know. Okay, there we got it. Okay, directional derivative in the direction of AC. Well, here's the direction of AC. What's the directional derivative? It's the rate at which the value of the function changes with respect to distance in the direction of AC. So what you do is you divide the change in the function as you go from point A to point C. Well, what's the change in the value of the function from point A to point C? The value of the function here is magnitude of the vector AP, and the value of the function here is the magnitude of the vector CR. The vector AC could be also drawn up here so that this segment is the same length as this segment, even though it doesn't look like it, didn't really draw it that way. meaning that this segment here, which is the rise of the PR vector, is the change in the value of the function. Okay, so the change in the value of the function is, well, delta z over the distance, magnitude of AC, and delta z, change in your z coordinate. Well, here again, you got the AC, you got the PR, here's your delta z. Delta z times k is your vector PR minus AC. So delta z over magnitude of AC is equal to the slope, which is the approximate rate of change. So PR minus AC over magnitude of AC is a vector which indicates the delta z. It's actually equal to delta z times k. And I probably should have had a k here and a k here, and so forth. Or if you want to make it a little better, just the length of PR minus the length of AC. Wait a minute, no. I wrote that down wrong. It's the length of PR minus I'd like to say I can't believe I wrote that, but I did. Okay, let me write it correctly. It's that's going to be wrong. I've got it backwards. It's CR minus AC, the length of the CR vector minus the length of the AC vector over magnitude of AC. Okay? And that is, here's your CR vector. You subtract the AP vector, and it's not AC, it's AP. So subtract this from this, you get this. That's the rise of your PR vector. That's your delta Z. So it's this over this. Okay. Now we got one more thing that we want to look at. Maybe two. A directional derivative in a direction of u is equal to the gradient dot u, my dot doesn't really look much like a dot, make it a little bigger. Okay, so gradient dot the unit vector, okay? I've indicated the gradient vector here in red. Now that gradient vector makes a triangle with its projection onto the y-axis. Okay, so this is all down in the YZ plane. I probably should have put the head on that vector in better perspective. It would look better. But this is all down, this red stuff is all down in the, I said YZ plane, in the XY plane. We're looking for the directional derivative of the function in the direction of the AC vector. Okay? Now I should have said directional derivative AC over magnitude of AC. This is supposed to be a unit vector here. And it does come out this way, and I did use the unit vector over here. Dot product of the gradient with AC, with the unit vector in the direction of AC. Now that dot product, if your unit vector, now if delta x and delta y are small, then a unit vector in the direction of AC might be miles long on the scale of this picture. I'm going to pretend, though, that the unit vector is just a little short thing here. So there's your AC divided by magnitude of AC. It's down in the plane. This is down in the plane. So we just project this onto this, And well, just take the magnitude of this times the cosine of theta, because the magnitude of this times the magnitude of this times the cosine of theta, and you get the length of this. That's a scalar projection. Then divide by the magnitude of your gradient, and you get the directional derivative, and you don't divide by the magnitude of the gradient. Okay. Anyhow, that's going to be a rate of change. And you don't really have to have a unit vector. If you do it with the unit vector, you get the length of this vector, and the length of this vector is your rate of change. Didn't say that real clearly. Let me say it once more now. Broke my chalk. That's pretty heartbreaking. The dot product of a unit vector in the direction of AC with your gradient, you just think of projecting your gradient onto the direction of AC, and the magnitude there is going to be this result, and that just comes directly from the definition of dot product. So kind of think it through. To say more about it, I have to write it out, and I don't want to mess things up by doing that. Okay, so another question. If P and R are on the curve, R of T, what's the approximate arc length on the curve between P and R? Okay, so that means these are on a curve. So you got a curve. And maybe that curve, it goes from here to here, but maybe it's kind of like this. Okay? And maybe it's not all on the plane here, and this isn't even a plane. It's a quadrangle, and it's not quite a plane. The approximate distance you would travel along this little arc, especially if delta x and delta y are small, so this curve stays close to this straight line, is going to be the magnitude of the vector PQ. Yeah. The distance from P to R, the magnitude of this vector, is very close to the arc length. So, say the length is approximately the magnitude of PR, which is the hypotenuse of a triangle with legs AC and CR minus AC. Here's AC, and here's CR minus AP, not AC, minus AP. There's your CR minus AP. There's your AC. So 2 ways of representing the length of that thing. That if you understand it, which if you understand will illuminate formulas for the arc length. Okay. Now there's more. Yeah, I'm almost stopped there. We relate things on this picture to things that we can notate in the notation of the functions. For example, the vector PQ. Well, that's delta xi, and then plus the rise. Well, the rise is from here down to here. Okay, what's the rise? The rise is x derivative times delta x. Okay, because the x derivative is the approximate slope. Okay, you multiply the slope by delta x, you get the rise. You get the delta y. In this case, the delta z. So PQ is approximately equal to this. You need to understand that. And PS, for similar reasons, is approximately equal to delta yj plus Fy delta y being the rise. If the slope is Fy, the derivative, y derivative, times your run, delta y, and that rise is in the z direction, so it's that times k. So what's the normal vector? I left a blank here. You really ought to fill in that blank. What's a normal vector? Now we've written this out, and we've written out what the normal vector is and how we get it, but apparently didn't take because nobody really understood all the details, okay? And that's not surprising. Incidentally, this big blue vector is something I drew that I shouldn't have, so just kind of ignore it. If I ask you what are the coordinates of the point P, well, it should be obvious, and we've seen it many times. P is the point x, y, f of x, y. Okay, because this is P is a point on the graph of the function, so you plug the coordinates of x, the coordinates x, y into the function, you get f of x, y, and that's the value, and that's the z coordinate. Okay, these are very fundamental things. Everything is built on these fundamentals, which is why we're going over them 2 days before the exam. Okay, similarly Q is what? What are the coordinates of Q? Well, here's Q. The x coordinate is x here plus delta x, and y, because the y coordinate hasn't changed, and f at x plus delta x, y. Might be hard to read that, but you put these two coordinates into f, and you always get the z coordinate, whatever these two coordinates are. Okay? R is what? Well, the x coordinate is x plus delta x. The y coordinate is y here plus delta y. So it's x plus delta x, y plus delta y. F of x plus delta x, y plus delta y. Another notation for the directional derivative of AC, directional derivative of f in the direction of AC, that is AC over magnitude of AC being the unit vector in the direction of AC, is f of c minus f of a over the square root of x squared delta x squared plus delta y squared. Why is that? Well, f of c is this, length of this segment. F of a is the length of this segment. So we do f of c minus f of a, which we did with vectors a little while ago. You get the rise between this point and this point. In other words, the change in the value of the function. So this is the change in the value of f. And maybe if I can find that blue chalk, where'd it go? Huh. Got another piece here. Don't want to lose that piece. Okay. This equals delta f over delta s, where delta s is the distance you move down in the plane, and delta f is the change in the value, this. Okay? That's another notation for your directional derivative. You want to understand all these quantities in as many ways as possible. And I'll leave you with that statement. Again, so I'm going to leave you with that statement. I'm going to make another one. But again, the reason I wanted to focus on the polytope is to focus on the most fundamental quantities that are behind arc length, tangent planes, differentials, gradients, directional derivatives, the stuff they're going to need to know for the exam.